So the binomial theorem in algebra is just an efficient way for us to be able to expand out binomial powers. Okay, so for example, x plus y squared expands to x squared plus 2x plus xy plus y squared. X plus y cubed, when we combine all the like terms, we get x cubed plus 3x squared y plus 3xy squared plus y cubed. Now, and for power 4, etc. Now, you may see some sort of patterns evolving here. One of the ones that you might see is this power on x seems to descend from 2, 1, and in fact, you can put power 0 there. For 3, it goes 3, 2, 1, 0, 4, 3, 2, 1, 0. And you could also see the reverse is happening for y. So the y's go 2, 1, 0, 3, 2, 1, 0, 4, 3, 2, 1, 0. Okay, so that's one part of the binomial theorem, is if you can recognize the pattern of the powers. But the other part of this is the coefficients. The coefficients happen to follow Pascal's triangle. So if we take a look at this row 2, we get 1, 2, 1. Row 3 gets 1, 3, 3, 1. Row 4 is 1, 4, 6, 4, 1. In fact, row 1 would be 1, 1, and row 0 would be 1. In fact, here's Pascal's triangle over here. And you can see that those coefficients show up in these powers. Okay, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. The next power, or expansion of power 5, actually just follows the 5th row of Pascal's triangle. Power 6 expansion just follows the 6th row of Pascal's triangle. So we can use this Pascal's triangle and the pattern of powers to help us expand these multiplications, these binomial powers. So I really would not want to expand this by doing a plus b, foiling that out, times b, foiling that out. We really just wanted to have a more efficient method of calculating this expansion. And to do this, we just use our 5th row. So I'm just going to go to my 5th row here. My 5th row is 1, 5, 10, 10, 5, 1. So I'm just going to go 1, 5. Let me write this a little closer together. 1, 5, 10, 10, 5, 1. Okay, and this allows me to get my expansion coefficients. And the powers on the power part of this is fairly straightforward. We get a to the power 5, b0, plus a to the power 4, b1. Notice that the powers always add up to the original power of 5, and it's in descending powers of a, increasing powers on b. So we get plus a3b cubed plus 10a squared, sorry, that's going to be a cubed b2. We get a squared b3 plus a1 b4 plus a0 b5. So there's our expansion. We don't really need the power zeros, but I just put them in there just to highlight the pattern of powers here. For power 6 expansion, we just go to row 6. Okay, so there's 7 terms in row 6. So I'm going to write my coefficients. It's going to be 1, 6, 15, 20, 15, 6, 1. Okay, and then I just use the pattern of powers to get the power parts here. So it's going to be a to the power 6, b0. In fact, I'm just going to leave the b0 out. We're going to get a to the power 5, b plus a to the power 4, b squared, plus a cubed, b cubed, plus a squared, b4, plus ab5, plus this is going to be b to the power 6. So there it is. There's my expansion. I don't have to FOIL out and combine a whole bunch of like terms. This all has the coefficients have the like terms all combined. This is a much more efficient way of doing this expansion now. So for power 3, in this case now, my a's and b's have other coefficients involved, and there's also a minus in there, so I have to be wary of this. So I'm just going to do my coefficients first. So it's going to be 1, 3, 3, 1. Okay, so that's my expansion coefficients for the third row of Pascal's triangle. Okay, so then doing the power parts, I'm going to have 2x cubed, and then it's going to be negative 3 to the power 0. I don't really need that part. I get 2x squared, negative 3 to the power 1, plus 2x to the power 1, negative 3 squared. And just going to move that over a little bit, plus my coefficient is 1. It's going to be 2x to the power 0, negative 3 cubed. Okay, and then I just simplify this expression. So this becomes 8x cubed plus, this is going to be 2 squared times 3 times negative 3, so that's going to be negative 36. So negative 36x squared plus, this is going to be 3 times negative 3 times negative 3 times 3 times 2, so that's 54. X to the power 1. Okay, plus that last term is going to be minus, it's going to be just 27. Okay, or negative 3 cubed. Okay, so this is how we can expand these without having to do all this FOIL and collecting like terms. So same thing here. This one here, I'm going to write my coefficients for the row 5. So 1, 5. I forget what this was again. 1, 5, 10, 10. Right? 1, 5, 10, 10, 5, 1. So 1, 5, 10, 10, 5, 1. Okay, so this is going to end up being 2 to the power 5 plus, okay, that's going to be power 0, so I'm just going to leave that out. I'm going to end up with 2x to the power 4, and then negative 5y over x squared plus, okay, it's starting to get a little bit crowded in here, so I just have to be a little bit careful writing this out. 2x to the power 3 negative 5y over x squared squared plus, okay, this is going to be 2x squared negative 5y x squared to the power 3 plus 2x, and then this is going to be negative 5y over x squared to the power 4 plus 1, and this is going to be negative 5y over x squared to the power 5. Okay, so I'll leave the 0 power out of that. So once I've done this expansion and filled in the parts, I'm just going to do my simplification here. So this is going to end up being 2 to the power 5. That's going to be 32x squared. And this is going to be minus. So I'm going to end up with 25 times 2 to the power 4, which is 16. So 25 times 16, that's going to work out to be 400 is my coefficient. I'm going to have x to the power 4 divided by x squared. So it's going to be x squared y. Okay. I'm going to do this one. I'm going to work out the coefficients first. So I'm going to have 10 times 8 times 25. So 8 times 25 is 200. And times 10 is going to be 2,000. So it's going to be positive 2,000. Okay, the power on x, we're going to have x cubed divided by x to the power 4. So we're going to end up with y squared on top, x on bottom. Okay, if I want to write x to the negative 1, that would work as well. In fact, maybe we should just do that. We can see the pattern a little bit easier. X to the negative 1, y squared. Okay, moving on to the next one, that's going to be 5 cubed. So negative 125 times 4. Okay, negative 125 times 4 is 500. times 10 is 5,000. Okay, so there's my coefficient. X squared divided by x6, I'm going to end up with x to the negative 4. Okay, and then y cubed. Moving on to the next one, that's going to be 625 times 2 is 1250 times 5. So 1250 times 5, that's going to give me 6,250. So plus 6,250. So we're going to have x power 1 divided by x to the power 8. So we're going to end up with x to the power negative 7. And you can see how the powers are going down by 3. And the y powers are going up by 1. Okay, so there is still the pattern. There's still a pattern of the powers being shown here. And then 5 to the power 5, that's going to end up being 3,025. And that's going to be y to the power, that's 10x to the power negative 10, y to the power of 5, and there's my full expansion. So that's a very big expansion. If you were to expand this out term by term by squaring this, this would have been a very difficult and time-consuming expansion. With the binomial theorem, it's still quite a bit of work, but it's much less work than if you were to expand this out using your distributive property.